Hello, I'm Neil Robertson, doing homework number 1 for Transport 2. In this problem, we have an enclosed capillary with gas A on the left side and gas B on the right side with a barrier in between. Once that barrier is removed, we end up with a mixture of A and B uniformly distributed at equilibrium. Using this scenario, we're going to come up with an expression with molar diffusive flux and mass diffusive flux that can be found, so that those two things can be found at any given point or at any given time. Now to start this, we're going to look at the relationship between total molar flux and total mass flux, no diffusion. We're going to start with total molar flux. We have total molar flux is the sum of the components fluxes, molar fluxes A and B. Now, what does that equal? That equals 0. But how do we know that? Well, first you have to look at the ideal gas law. It gives you the moles over the volume equals pressure over the constant R and the temperature. Now, R is constant, and we're given that pressure and temperature are also constants. So the whole right side is a constant number. Now, the left side, the volume, since the space is enclosed, has to also be constant and cannot change, meaning that the moles throughout the whole thing has to be constant. So, when you have the molar flux of A going right, it has to be canceled out for the molar flux of B going left, meaning that these cancel out to equal 0. Also, it can be seen as from a specific point, the end point you have right there, there can be no moles flowing through to the left because it's enclosed, so it has to also be 0 to give a constant canceling out. So, with that information, we're going to look back at the relationship between the total molar flux and the total mass flux, which would be the relationship between moles and mass, or molecular weight. You have the total mass flux equals the molecular weight times the total molar flux. That's the relationship between those two. But would it work the same for components of A with molar diffusion flux and mass diffusion flux? It doesn't. So we're going to have to look at another way to view this problem. We're going to use equations 1.18, molar diffusive flux of A equals concentration of A times the velocity of A minus the total molar velocity average, distinguished with the bar over top, and 1.17, the mass diffusive flux of A equals the density of A times the velocity of A minus the total mass average velocity. Now, how can we simplify one of these equations? We're going to look right quick back at the total molar flux, which can be given in another equation. Total molar flux equals the concentration over the velocity, the total molar velocity average. We know that equals 0 from before. So, when you have two things multiplying, we all know that one has to be 0, at least one. So, if we look at the concentration in this scenario, we have concentrations A and B enclosed in the capillary. So that can't change. We have to have some sort of concentration. So, that means total molar velocity average has to be 0. We're going to insert 0 up there, simplify the equation of total of molar diffusive flux of A equals concentration of A times the velocity of A. Now, look at this, pretty simplified. We see we have velocity of A here and there. So we're going to put velocity, solve for velocity of A, and insert that into the equation over here. We get the mass diffusive flux equals the density of A times molar diffusive flux of A over the concentration of A minus density of A times the total velocity mass, total mass velocity average. Now, if we look at what we just plugged in, we have concentration, we have density over concentration of component A. Now, density is the mass of A over the volume total. And the concentration would be the moles of A over the volume total. So, volume total cancel out, you have, and since those are over top of each other, you have mass of A over moles of A. And that is the same thing as the molecular weight of A. So we'll have mass diffusive flux, molecular weight of A times the molar diffusive flux minus the density of A times the total mass average velocity. Now we're going to look at the other side of this equation, density of A times the total mass average velocity. Now, can't do anything with the density right now, so we're going to look at the total mass average velocity. Its definition, that it's the sum of the components, which is the density of A times velocity of A, change up how it's writing A, fix that, plus the density of B times the velocity of B over total density. Now, we know that this is the velocity of A. The same thing is going to happen if we were to do velocity of B. We get the molar diffusive flux of B and the concentration of B. So we're going to insert both of those into this equation, and at the same time, using this example right here, that ends up being the molecular weight of the component times the molar diffusive flux of the component. We're going to simplify to that. So you have velocity, total mass average velocity equals molecular weight of A times the total, the molar diffusive flux of A plus the molecular weight of B times the molar diffusive flux of B over density, total density. Now, with that simplified, we're going to insert that back into our original equation here. So, we get mass diffusion flux equals molecular weight A, molar diffusive flux minus density of A times molecular weight of A times the molar diffusive flux of A plus the molecular weight of B times the molar diffusive flux of B over total density. Now, we notice that now we have a molar diffusive flux with component B, which we don't want. So we have to understand the relationship between molar diffusive flux of A and molar diffusive flux of B. Now, it's very similar to this, or the same as this, where you have the components are equal and opposite. So we're going to insert negative molar diffusive flux of A for molar diffusive flux of B. And you have to remember to keep the negative sign, which will make the addition subtraction. Now, we have one last thing to do before we take out the molar diffusive flux of A. And that's density of A over total density. Now, just like above, we have density A, just mass A over volume total, and density equals mass total over volume total. Cancel the volumes and you get mass of A over total mass. Now, with that, we know that the mass of a component over the total mass is the mass fraction of that component. So, with that, we're going to plug that in back into our equation, and we're going to take out the molar diffusive flux. So we get, I'm going to write this in red, so this is going to be our answer. If red wants to write, which it doesn't. We won't be writing it in red. We'll write it in a different color. Try green. Mass diffusive flux equals the molar diffusive flux times the molecular weight of A minus our mass fraction of A times our molecular weight of A minus our molecular weight of B. And that, even though there's lots of molecular weights in there, is our expression. Since molecular weights can be found throughout the periodic table, as long as you know what the gas's molecular formula is. So all you need to know to use our expression to find the molecular or mass diffusion flux at any given point, at any given time, is 2 out of 3 of these components you need, or the weight, the mass fraction of A with one of the other 2 to find the other one. And that, we're done.